Okay, any questions? So. Okay, so today we're going to talk about complex itemizing, and if we make it, you see, we might get a little bit into the next section here. So if you have a matrix, to find an eigenvalue for any n by n matrix of R, what do? Evaluate determinant A minus lambda I, and you set that equal to 0. And of course, this piece right here, when you roll it all out, work it all out, this is a degree in polynomial. In the variable lambda. And so what you have is an nth degree polynomial, set it equal to 0, and you try to find solutions to that. Now, here's the problem. Real polynomials do not always have only real solutions. Right? For example, but one thing that is true is every degree n polynomial has n complex solutions, right? So if you allow complex, so are you all familiar with this? You saw this kind of equation for a complex. If you have a real polynomial, complex roots come in conjugate pairs, right? Well, so that's what it will look like here. There's really not a lot of difference here, but I'm going to show you some things that you can do to kind of manipulate and some special things that happen with this kind of rotational matrix. So let's start with an example. I'm not going to bother in this first example. I'm not going to bother with the eigenvectors yet. I'll do that next time. Does anybody remember what this matrix does?
Rotates clockwise 90 degrees.
Well, actually, this one I think is counterclockwise, and it's theta rate, right? So, for example, you put in power 2 everywhere here, and you would get counterclockwise 90 degrees. Now, this matrix usually does not have real eigenvalues. It doesn't one except well, 2 except. Let's figure out what the eigenvalues are. So if we were to do this, we look at determinant. Well, I'm going to get lambda squared minus 2 cosine theta of lambda. Right? That looks like plus cosine squared theta plus sine squared. And this has a simpler name. I like to call it 1, right? And then, of course, we can set the sucker equal to 0. Now, This may look horrible, but it's not too bad. It's all you really need is the quadratic formula. So let's see how this goes down. So at this juncture, we will apply the quadratic formula. To obtain my square root of this square minus 4 times 1 minus 4 over. And I can simplify this a little bit. Let's see, 2's cancel here. So I have 2 eigenvalues. Right, so I can pull this 4 out and under the radical, that's we'll bring that out of the radical. It's 2.
There'll be a 2 outside of them.
Which cancels that.
What of the first two?
What's that? Cancels out. Now, what can you say about what's under the radical there? Actually, it is negative sine squared, right? So that's an interesting observation. I like that. So what can you say about what's under the radical there? It's usually negative. And there's an exceptional case. Notice that. This sector is never positive, right? Because it's a negative square. The biggest it can ever be is 0. Etc. If theta is any multiple times 0, in which case we get real eigenvalues. If this is 0, then the real eigenvalue you get is cosine theta. 1 if theta equals 2 pi k. That is, it's a multiple of 2 pi, and it's negative 1 if theta is 2k plus 1. That is, it's not a multiple of pi. And in this case, my original matrix is either plus the identity or minus the identity, right? Because in the original matrix, say cosine theta, that's either a pair of 1s or a pair of negative 1s equal 0s, right? But in all other cases, for all other values. Theta. This matrix has complex eigenvalues. And they are cosine theta plus or minus I sine. Basically. Everybody agree? And by the way, lots of times people, it's really unfortunate that I is called an imaginary number. Actually, in a certain sense, I think I is on much of a firm footing in numbers like E and I, philosophically, my point of view. However, this is used a lot in real math, used a lot in engineering. I is used a lot if you're an electrical engineer or in computer science, you see this quite a bit as well. This is actually important use of this. I don't know how many of you all saw this. Trigonometry, calculus. Anybody know what that is? E to the I times theta. Well, no, it's various theta varies. How many of you have ever seen that identity before? Sometimes you've seen it. You probably have seen it. How many of you have seen this? Calculus? Maybe you've seen that. How about this? Seen that in calculus? If the super sign goes on. Let's come back and bite. There you go. Replace X by I theta here, and it will split up into this series and I times this series. Check it, you'll see. This is a very fundamental thing. It relates the exponential trig functions. It's not a coincidence. This comes up here, right? And it's the reason. How many of you covered in calculus the hyperbolic cosine and the hyperbolic sine? This also gives a connection there. We can do that as well. So, but anyway, despite the fact that we call I imaginary, it is rather important. It shows up in if you've had differential equations or going to have it up, it shows up in solutions to real differential equations as well. Let's do one where we actually compute some. Yeah, let's compute that. Yeah, so here's kind of a normal example here. Find eigenvalues and eigenvectors for the matrix. Comes out okay. 3 minus 5. Okay, so let's now the procedure for finding both eigenvalues and eigenvectors is the same. The only difference here is maybe the solutions can be complex. And I'll show you how to handle the eigenvectors. The procedure exactly the same. In fact, we'll give you short ones. Okay, so let's start with this matrix here. First, let's get its eigenvalues. So get the eigenvalues. We will determine this. They determine this. And this comes to lambda squared. Plus 3 minus 3 lambda minus 9 plus 25. And I'm gonna set the sequence. So here I get some simple. There are my complex conjugate eigenvalues. Now, what do we do to find the eigenvectors? We do the same thing we did before. We just subtract that from the diagonal, each eigenvalue from the diagonal, and find the null space. And the manipulations are essentially the same. So the eigenspace for lambda equals 4i. So I'm going to do 4i eigenvalue now. So I'm going to subtract that. And what I'm doing for here is now I want to find the null space of this, right? Now I know this looks like that on a hot plate, but there is a shortcut. This is an honest 4i is an honest to goodness eigenvalue. So what must be true if this has a non-trivial null space? What must be true about those two rows? So this is going to just save me a little computation, but this row should be a multiple. Doesn't look like it does, right? But it is. Let me check this. So it's probably worth checking this one. Check. Let's see. Let me do it this way. What do I got to multiply? It's negative 5 by to get this. Well, I need to multiply negative 5 times something to get 3 minus 4i. Right? And well, I bet it's minus 5. Right? Nothing up my sleeve. Do I agree with that? So if I multiply this by whatever that graph is, then that should make these match, right? Now the big question is, does it work here? All right, well, test it. Let's see if this also, so I multiply this by this, and I get this thing right here. Let's make sure the multiplying this by this gives me that. All right. Well, let's see. 3 minus 4i over negative 5 times minus 3 minus 4i. Let's see what this is. The minus is canceled. That'll make this a little bit easier. 3 minus 4i times 3 plus 4i over 5. Well, if I multiply this out, this is going to be 9. Middle terms vanish, plus 16 over 5, 5. Exactly. That means these two rows are essentially the same, right? This one's multiple of this one. Right? This makes it easier for me to, so I'm going to have, I can treat this like a row of zeros now, because this row is multiple of this one. And so I get the following equation. X2 is my free variable. My eigenvector should look like this. And X1 is minus 5 over minus 3 minus 4i. 5 over plus 4i. 1. Yes,
There, that 5 is positive on X.
probably. Yes, let me take that over to the side. Thank you for catching that. That should be a positive. And so that should be a positive. And well, so I'll make that negative here, but that positive. So here's what I get. So the first pair I get is 4i, and my linear independent eigenvector is -5 and 3 plus 4i. And all I did to go from here to here is I multiplied this vector by the denominator here, just so I didn't have that fraction. But you can leave it this way if you so desire. What about the other eigenvalue? Now I subtract -4i from this. So that's going to give me the matrix -3 plus 4i -5, 5, 3 plus 4. And again, this row is multiple of this one. And so I'll be more careful this time. I get x2 is 3, and I get -3 plus 4i. X1 is 5, x2. And so I get the eigenvector 5 over -3 plus 4i and 1. So the eigenvector pair I get here is five. Or again, you can leave it this way, whatever floats your boat, it's all good. So really, there's no difference in all of the computations at all. And if you wanted to get on your horse and drive, you could just bring this to row and do echelon form. The only difference is now you're adding, subtracting, multiplying, dividing by complex numbers, which is just a little bit more complex, not just real numbers. Okay. Any questions? Okay. Given the vector P, C, N. So now I've got a vector that instead of in real integers, it's got in complex integers. I can divide it into this real and imaginary. And I'll kind of do this here. So if I give you this vector here, consider B and C4. Let's say that B is this. 1 plus I. 2, 3i, and 5 plus 7. Notice that I can break B up this. This is like 1, 2, 3, 5. And that's just pulling all the real, no, it's not, 1, 2, 0, 5. 1, 2, this is 0 plus 3i. So think of this as 2 plus 0i, 0 plus 3i, 5 plus 7i. I pull the real parts off. And then I pull out I stuff. 1, 0, 3, 7. And this bit right here is called the real part. And this part here, even though it's real, it's called the imaginary. And sometimes we write it this way. We would write for this example, the real part of B would be 1, 2, over 5. And the imaginary part in this case would be 1, 0, 7. So when I tell you the real part or the imaginary part, you're just pulling those components out. Let me give you another observation. So, any questions? If you have a complex number, that is to say, A and B are real numbers, and I is supposed to be 1. Then A plus B I with bar over is complex number. So this is binary. So you just change the sign of the imaginary part. Note that in C, then C bar notice that when you multiply a number by its complex conjugate, you actually get a real number. And not only do you get a real number, you get a number that's greater than or equal to 0. And in fact, the only way that this is 0 is both A and B are 0. That's actually going to be important when you talk about the inner product here soon. Let C1, C2, and AB of the complex numbers. By the way, let me point out that any real number is a complex number, but not every complex number is real. But C1 and C2 be complex numbers, and let A and B be complex makers. Number 1, C1, C2 are So the complex conjugate of the product is C1 bar. So basically what this says is you can multiply the two numbers first, take the complex conjugate, or you can take the conjugate of them separately and then multiply them, you get the same. Number two, if you multiply the matrix by some complex number, take the conjugate, this is C1 bar, A bar. And what I mean by the complex conjugate of the matrix is you just go through the matrix and take the complex conjugate of all the elements. Yes.
So, if you multiply Z1 and Z2, if it turns out to be a real number, then how would you take the conjugate of that?
It's the same thing, right? So, for example, so the question you asked is this: what if B is 0? Right? Well, when the complex conjugate of complex conjugate of B of 0 is just, that would just be the complex conjugate of A, which is X. Yes.
In the definition at the top, where it says if A plus BI and complex number of A plus BI is not supposed to be the same. I'm just really confused. Like, just because the line above it not makes it.
Yeah, A plus BI is a complex number, then A plus BI with a line over it is the complex conjugate. And this is the way it's defined: A plus BI with a line over it is A minus. Does that make sense? Number 3, if you take two complex matrices and multiply them and get the conjugate, it's the same as taking the conjugates separately and multiplying them. And from this, well, I'm gonna actually prove statement 1. And the rest of it follows this, and it's easy to do. But Z1 equal A1 of B1I. And Z2 is A2 of B2I. Notice that. So let me just list all the players here. Z1 bar is A1 minus B1I. Z2 bar is A2 minus B2. And let's see what else I need. Z1, Z2. A1 B1I. A2 plus B2. And we'll see what happens. This is A1, A2. And then stuff divides it. A1, B2I. A2, B1I. And then the product of these B's is minus B1, B2. Because the I squared is negative 1. So this turns out to be A1, A2 minus B1, B2 plus I times A1, B2 plus A2, B1. Okay, so let's grab it and grab. Z1 bar times Z2 bar is A1 minus B1. A2 minus B2. And this product is in a similar fashion. We have 4 A1, A2. That's real. Multiply these two and it'll be real. It's going to be B1, B2 times negative 1. equals I times A1. Well, this can be minus A1, A2, minus A2, A1. So this is A1, A2, minus B1, B2, minus I, A1, B2, plus A2, B2. And notice, this is the complex quantity. Proofs of all these others are very simple, just more long. Okay. Okay, any questions? Okay, so let me point out a fundamental matrix. Remember, notice the determinant of this matrix is 1, right? Because the determinant is cosine squared cosine squared 1. So in a certain sense, we're going to see more about this later. This means it sort of doesn't affect the length of any vectors. Now, what this matrix does is it actually rotates a vector by angle theta in counterclockwise fashion, right? I'm going to show you a matrix that kind of generalizes this. So you'll probably see some similarities, only it's not just based on cosine and sines, it involves some stretching now. Here is fundamental type. And you'll see what I mean by fundamental in a moment. Here, A and B are real numbers, not total. I don't want them to zero matrix because that would be very silly. Now, notice that, well, something out here. Notice this kind of has this thing here. Notice how the diagonals are parallel, right? Same as here. And the off diagonal ones here are off by a sign. Only nobody said, and this matrix is special because the square of this plus the square of this is 1, right? Nobody said the square of this plus the square of this is 1. But there are connections. The first one with the sines and cosines is a rotation matrix. It doesn't change the size of any vectors. And this one's sort of just a little bit more general. If you look at this matrix, this has eigenvalues. A plus or minus BI. As it turns out. I'm going to read that as an exercise. See if you can figure this out. This would be a good little exercise to show you this is eigenvalue A minus BI. So let me point out, just like our first example, this usually has complex, not real complex conjugate eigenvalues, except in one exceptional case. When does this have real eigenvalues? When B is 0, this has real eigenvalues. Well, what does this matrix look like when B equals 0? It's just diagonal, it lays on the diagonal. Do I agree with it? Okay, and let me make another observation. And this is what's kind of special about it. If R is the complex magnitude of lambda, which is the square root of a squared plus b squared, then I can rewrite this matrix this way. This is R. And actually, now it's kind of cool because now, remember how I said nobody expects a squared plus b squared to equal 1, but in this matrix here, it does. Because if you square this, you get a squared over r squared plus b squared over r squared. So you get a squared plus b squared over r squared, but a squared plus b squared equals r. And so this is actually a matrix that looks like this. This is actually a cosine minus sine, sine, cosine. And take this out a little bit further here. This is actually cosine theta minus sine theta, sine theta, cosine theta. So to identify this in terms of sines and cosines, how do you do it? Well, I'm going to tell you how to figure out what the angle is. This might not be a surprise. If I draw a little triangle here, and I think the real part as A and imaginary part as B is theta, and here theta is the inverse tangent of B. Notice that if you take this theta and take the cosine of it, you will get A over R, right? Because here, the hypotenuse of this triangle is R, which is the square root of A squared plus B. So for example, when I take the cosine of this angle, the cosine is A over R, which matches right here, A over R. So, in particular, what's important about this fundamental type of matrix? Well, a matrix like this can always be decomposed into this piece, which is basically just multiplication by R. It's a stretching piece that just stretches it, or if R is small, contracts it, and a rotation. So basically, this type of matrix is doing two things. Doing a spin and then doing a stretch vectors. Now, okay, why is this fundamental type important? Well, A, because it's a rotation and then it's a stretch, but also because if you have a matrix with non-real complex conjugate eigenvalues, then it turns out that basically you can make it be similar to a matrix that looks like this. So let me give you this theorem. So suppose I have a 2x2 real matrix with the complex conjugate eigenvalues. Which, if there's a single non-real eigenvalue, they have to be a complex conjugate. They're a real matrix. Yeah, we select if we select the eigenvalue A minus BI, and B in CP is its eigenvector. So take this eigenvalue and just call this the negative B eigenvalue, compute its eigenvector, then A is similar to the matrices form, PCP, where here are the players, P is the real part of the eigenvector B and the imaginary part of the eigenvector B. And C is A negative B. Okay, so let's see this in action. And then I'll give you an example. Let's do this matrix here. So let's apply this theorem to this matrix here. 19, 29, minus 13, minus 19. Now, if you compute the eigenvalues for this, then what I get here is lambda squared. When I take the determinant of this, I get lambda squared minus 19 plus 18 lambda, so that's gone. I get like minus 361 plus 297, 377. Which is lambda squared plus 16. So I get two eigenvectors. I get lambda is 0 plus or minus 4. So let us pick, we can pick either one of those eigenvectors. So let's pick lambda as 4i. Let me point out that this choice is arbitrary. You can pick the other one, right? But to use this theorem properly, we'll see I picked 4i. So here in the theorem, we have p is negative 4. Because this is lambda is 0 minus 4i. So in our theorem here, this is minus 4. So let's do the eigenvectors. We'll see, I've got to subtract 4i from the diagonal, so I get 19 minus 4i, 29 minus 13, and then minus 19 minus 4i. Now just as before, you can row reduce the matrix if you like, if you like to do this. However, this row is a multiple of this row. So I'm just going to go ahead and take advantage of that. So I get 19 minus 4i x1 plus 29 x2 is 0. And x2 will be 3. And so I get an eigenvector that looks like this. X2 and minus 29 of 19 minus 4i. What x1 is. So I get the following eigenvector. I'm going to simplify this again so I don't have to write these crazy fractions. I get minus 29. And then I get 19 minus 49. Everybody with me so far? This is the eigenvector corresponding to the eigenvalue for I. So this tells me how to build my P. My P should be the real part of this, and then the imaginary part of this. Did I put that all right? Okay. Everybody okay so far? Now I only need to figure out the inverse. And I'm gonna do this quickly. You can roll this so like, but this is a lower triangle matrix, so its inverse has to be lower triangle. And I immediately know that the inverse so the inverse of this should be minus 1/29 minus 24, and this should be something like 19.116. That works. 1 mil minus. Yep. Oh, wait a minute. It's going to be minus. Yep. Now let's check. If you check it, my matrix C here should be let's see, B is -4, so that should be 4 minus 4, and then my A is 0, isn't it? And so let's do a multiplication here. And well, so I've kind of run out of time here, and I apologize for that, but check that in fact A is equal to B, C, and but that's how you do it. The real and imaginary parts of your eigenvalues, the inverse of the matrix, you conjugate this matrix here. And you get that. Okay, any questions on that? Yes, sir.
With the eigenvalue thing on the left of this board, is there any way that we can assume that they are multiples of each other, or just,
Oh, okay, which eigenvalue you talking about?
or that matrix? Yeah, you said that those two rows are multiples of each other. How do we figure that out? Just
Well, because of the fact, you can do it brute force, okay? The reason I know this is because it's only 2 by 2, and I know this is a legit eigenvalue. That means the null space is not trivial, which forces this row to be a multiple of the other one. But for example, to get this to match up this, multiply this by 19.4 over 29 and add it here, and you get the same thing. Any other question? Yes.
That all cases, once you have a imaginary part, there will be non-trivial.
Well, if you have a 2 by 2 matrix and it's got a non-trivial null space, that means one row has to be a multiple.
There will never be a case that is.
Or that's in general true for a 2 by 2 matrix. Yeah, for larger matrices, it's more subtle because you can have linear combinations.
how do we get our C matrix?